All right. Okay. We start off with a transfer function. So a transfer function, in this case, you can see in the equation 2.5 here, we have the general order and order of linear time invariant LTIV differential equation. So we have A dn ct over dtn plus a n minus 1 dn minus 1 ct over dtn minus 1, and so on and so forth. So in this equation, we have the ct here is the output, and rt here is the input, and a, b, and are the coefficients of the differential equations that represent the system. So now you have learned about Laplace previously in the two videos. When we taking the Laplace here, we have an is a constant, so it does not change at all. So we have here we have the nth order of ct over dt. We have cs, and then we have sn order, sn, and then plus initial conditions terms that involving the ct, as well as the other side of the equations. We have a bm sm rs plus the initial conditions that involving the, I think it's this one is rs and rt here. So if we assume all initial conditions are 0, so we can have equation 2.52 here. Okay, so the transfer function of the system is, we can say, this output over input here is gs equals to these terms. Okay, so the system output could be obtained using cs equals to gs and rs. So the next one, the transfer function can be presented in the block diagram here. So we have the input here, and then we have the output here, cs, and in the middle, in the box here, this is what we call the system and the plant. So inside this is actually a GS, all right? So it's actually GS. Okay, the roots of numerator is called 0. So this one, this is the numerator, and then this is the denominator. We call it poles. Okay, numerator zeros, and denominator is poles. Okay. So let's see example 2.4 here. So find the transfer function represented by equation 2.55. We have dct over dt plus 2ct equals to rt. So solutions, we're taking the Laplace transform of both sides. So we take the Laplace transform of the left-hand side and the right-hand side, assuming 0 initial conditions. Whenever it's not mentioned, so we assume 0 initial condition. So assuming 0 initial condition, we have this term dct over dt is scs. And then we have 2ct is 2cs. And RT is RS. So if you have no idea how I get this in this example, please refer to the Laplace transform video in the Google Classroom. This is very important. Okay, and then the transfer function here can be, you just algebraically arrange them, and then you have a CS over RS equals to these terms. Okay. Any questions? So far, okay? Please stop me whenever you feel I'm a bit fast or you need some explanation, okay? Right, next one. Another problem. So use the result of example 2.4 to find the response CT to an input RT unit step, assuming zero initial conditions. Okay? To solve the problem, we take the previous examples here. We have in the previous examples, you know that the output can be found by multiplying input to the GS, RS multiplied by GS. So in this case, we have the RS is, in this case, RS is the unit step. Okay, a unit step meaning you have the unit step is, you can refer to the Laplace table. A unit step is 1 over S. A unit step is 1 over S. So in this case, our RS equals to 1 over S. Okay, and then our GS is actually from the previous examples, we have GS equals to 1 over S plus 2. Okay, 1 over S plus 2. Okay, so the output is CS equals to RS GS equals to 1 over S plus, sorry, S plus 2. Okay, so by expanding the partial fraction, this one you can get in the video of Laplace video, you can get how we can expand this term into this term. Okay, basically what we have is actually we have A over S plus B over S plus 2, right? A over S plus B over S plus 2, and then you can find the value of A and value of B. And then in this case, the value of A is 1 over 2, and the value of B is negative 1 over 2. And then finally, checking the inverse Laplace transform of each term yields Ct equals to 1 over 2 minus 1 over 2 exponential of negative 2t. Okay? So we already solved the questions in this problem. Any questions so far? Okay, I assume everybody is okay. Now, so I have covered the basics for the transfer function. Okay. All right. So just remember the transfer function is actually a ratio between the output to the input. CS over RS equals to GS. They call the GS is the transfer function. Okay, now let's go to the block diagram. All right, so the basic components of a block diagram for the LTIV system, we have signals, we have systems, we have summing junction, and we have pickup points. Okay, for the signals, remember the input and the output. Okay, input, output represent the signals. Okay, so the signals in this case represented by arrow. Okay, so this is the input, this is the output. Okay, next, for the system, a system is a combination of the input, the output, and the transfer function here. So you have the input, you have the output, and you have the transfer function, GS in this case. Okay, next one, we have summing junction. So this is the summing junction represented by the circle and X inside. Sometimes you will also see the summing junction, something like this, the summation inside the circle. So this is the circle, this is the summation symbols. similar. So this is plus, plus, minus, for example. Okay. All right. This is a summing junction. So in the summing junction, let's say we have a signals input R1, R2, and R3 here. So in this case, the output is the summation of all the inputs. So consider all the signs here. So R1 plus R2, so this is positive R1 plus R2 minus R3. So it depends on the sign that go into the summing junction. So we have positive, positive, negative here. So this is the summing junction. And then the last one, we have peak-off points. Okay, peak-off points. For the peak-off points, we have, for example, here we have the signal RS. Okay, signal RS. And then the signal RS is divided into another 3 signals. So we have 1, 2, 3 signals here. Okay, so whenever there is a junction of peak-off points here, so every branch will have RS. Okay? For example, in this case, RS, RS, and RS. 3 RS each on every branch. Okay. So keep in mind all the basic components of the LTIV system. So now you already know about the basic components. Let's go to the closed loop system. So for the closed loop system, I already mentioned in the video, in the first video, introduction video, we have open loop system, and we have the closed loop system. Okay, so the open loop system is a system that do not have feedback. Okay, otherwise the closed loop system is a system that consists of forward path as well as the feedback path. So this is the closed loop system. So the transfer function of the forward path is usually represented by GS. Okay, and the transfer function of the feedback usually denoted by the symbols of HS. Okay, so now the ratio of the feedback signals BS, so this is BS here, so the ratio of the feedback signal BS to the actuating error signal ES, BS to the ES is called the open loop transfer function. It is called open loop transfer function. Right. So this only take into consideration of this circle only. So ES to the BS. So the system involved is GS and HS. So we can write BS over ES equals to GS HS. So this is open loop transfer function, or you can say that loop transfer function. Okay, we can say that this is loop transfer function. Okay, and next one, the ratio of the output to the actuating error signal ES is called feed forward transfer functions. So we only consider the CS and the ES. Okay, so in this case, the feed forward transfer function is represented by C and E, C and E, which is only GS inside. So we only consider C and E. So in between, you only have GS. So feed-forward transfer function is E to C. So we have GS here. Okay. Next one. If the feedback transfer function HS is unity, then the loop transfer function or open loop transfer function and feed forward are the same. Okay, so previously we have the open loop transfer function is GH, right? So if HS equals to 1, then we have open loop equals to feed forward, which is G equals to G, because H is equals to 1 here. Okay, next one. Next term is the transfer function that relating CS to RS is called the closed loop transfer function. So it relates the closed loop system dynamics to the dynamics of the feed-forward elements and feedback elements. So we have already defined the feed-forward open loop. Now we want to consider all of them into our closed loop transfer function. So in this case, we have CS is related by G and E. Okay, this is the forward transfer function. Remember, the forward transfer function is it is actually the C over E equals to G, right? So this is a forward transfer function. So you have C equals to G and E. So this one. All right. So next one. So now that we have this, we consider E. E is the error. Error is R plus B. So R plus B. So in this case, B symbol is negative. So we have R minus B. Okay. Now that we know B is actually equals to CH. Okay. B is equals to CH. Okay. C and H. So we can take this equation, E equals to RS minus CH. Okay, and then we can put into this equation. You have CS equals to GS, where we have E here is RS minus CS HS. And the rest is only algebra. You can rearrange the equations. You can get, finally, the closed loop transfer function is represented by this equation. Okay, so you need to memorize. This is very important. When I say the closed loop transfer function, you must remember the transfer function is given by GS over 1 plus GSHS. Okay? One thing to note that you must see the symbol here. So this is positive here is actually a contra with the signal's feedback path, a sign of the feedback path. So whenever this symbol is positive, for example, whenever the symbol is positive, let's say this one positive. So your transfer function now become GS over 1 minus GS HS. Okay? Any questions so far? Macam mana dapat ES? Ni ya. ES ES is actually error signals. ES is error signals. How do you get error? Error, what is error? Error is what you want, what you get, what you want minus what you get. Okay, for example, you want the temperature of the aircon system is 25 degrees C. So what the system give you, what the aircon give you. Okay, so let's say the aircon give you 25 degrees C. So 25 minus 25 equals to 0, meaning the error is equals to 0. For example, now the aircon give you 27 degrees C. So what is the error? The error is 25 minus 27, which you get negative 2 degree difference. That is the error. So in this case, in the block diagram here, the error is denoted by the symbols ES. So what are the error? The error is what you want, RS, minus what you get, BS. Okay, what you get is BS. In this case, BS is actually the output multiplied with the transfer function of the feedback. So BS is actually CSHS. So you get error by giving summation of this input, desired input, with what you get, the actual output, BS. So you get ES is equals to RS minus BS. Okay tak Mahfuzah? Okay, what else? What other question that you want to ask? This is a very important concept because we will use it from now onwards towards CO4. Make sure you understand this. Okay, so I will explain a bit about cascade or series subsystem, and then you can later study at your own time, this one. So in this case, input minus output equals RS to desired input conductor. Yes, the error is always input minus the output from the feedback. Output from the feedback. So RS minus BS. Okay, Hakimah, Usna? Right. Right. So we have cascade or series subsystem. Okay, in this case, we have 3 subsystems. We have G1, we have G2, we have G3, and then our input is RS. So in this case, it is in series, in series, or we can say in cascade. So the output of the first one, we call it X2, is equals G1 as RS. G1 as RS. So the next one is we have G1 as RS multiplied by G2. So we get G2, G1, RS. Okay, and the next subsystem, since it is series, we multiply to G3, which will give you G3, G2, G1, RS, which consists all of the subsystem and the input. Okay, so it gives you the final output. You can represent it in a simplified block diagram. In figure B here, you have the input, you have the output. So the transfer function inside is G3, G2, G1. Understand? This is very simple. You just multiply every subsystem, G1, G2, G3. Okay. Next one, parallel subsystem. Remember the peak of points, okay? So the system represented in as the parallel system here, you have RS as the input, and at each branch you have a subsystem G1, G2, and G3. Okay, so the output of each subsystem is a multiply of R to the subsystem, which in this case R G1, R G2, R G3. Okay, and then at the end of the branch we have a summing junction here. So the signals can be positive, negative, positive, negative. So it depends on the signals, actual signals. Okay, so in this case we have the summing junction, meaning that you sum all the branches together. So what we have is we have R G1 plus R G2 plus R G3. So you can simplify by factoring R. So you get G1 plus G2 plus G3. Okay, and you can represent the simplified block diagram in figure B here. So you have input RS, you have output CS, and you have the simplified subsystem of G1, G2, and G3. Okay? All right. Okay, before we go to feedback form, I need you to really understand the cascade and the parallel form of the block diagram. So in this case here, we have the input RS, okay, and then we have a subsystem G1. It goes into a summing junction that take into consideration the output of this subsystem here, R1, R and G1 into the system, and the feedback into the summing junction here. That is actually the actuating signal or error here. And then it goes to the controller, plan, and the output, CS. So this is where we have the feedback path. Okay. All right. So in this case, we can simplify this block diagram by using the cascade or series. G2, G3 becomes GS. Okay. And then we have H2 and H1 here become H. Okay, and actually we can move the input transducer inside. Only left outside is the input. How to do it? Well, before that, this is the simplified diagram of the feedback transfer function. Okay, so we have G over 1 plus minus GH. So plus minus here, you see the difference in the sign. This is plus minus, this is minus plus. Take note on that. Okay, so you have learned about the feedback control system, the simplified model, and the equivalent transfer function here. So, and in the next topic, I will give you, or I will teach you about moving blocks to create familiar forms. Moving blocks to create familiar forms. So your homework is to read these lecture slides of moving blocks here and try to get familiarized yourself with the notes before I give you the lecture on Thursday. All right, so we end here. Any questions? So no questions. So please go back, read the notes before